Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy, established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries and whosoever seeking knowledge and information about various subjects and topics of metallurgy, operational process optimization, productivity improvement analysis, concepts like 5S, total productive maintenance, TPM, quality circle, QC, root cause analysis, RCA, ISO systems, QMS, EMS and OSHAs, practical and effective communication English, written and spoken. This is the foundation stone of forming this channel. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, you might have heard that training is costly, but not to train is still costlier. So do get your employees, colleagues and students trained on the relevant topics so that they perform well on their duty and subsequently contribute positively to the growth of your company and organization in a better way. So do contact me as soon as possible for organizing the sessions and get them trained. Dear friends, another important aspect of Knowledge Galaxy is that specialized subject-wise coaching classes are available for Diploma Engineering, Metallurgy and Mechanical, IIM, Indian Institute of Metals, Part 2 or Section B, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies. Metallurgical industries, here complete syllabus coverage will be offered for the students aspiring to appear in the forthcoming semester exams, that is December or June. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes via video conferencing. My dear friends, now the technology has improved so much that actual physical distance doesn't matter anymore. You can get your doubts clarified and clear all your doubts and gain knowledge by sitting at your home or office or wherever you are comfortable with. So use the technology and get your doubts cleared. Do contact me as soon as possible. In my previous video of equilibrium diagrams part 1, I have discussed in detail about the classification of equilibrium diagrams or phase diagrams. In that video, I have discussed in detail about the isomorphous system. So the link of that video is available on my channel. You can visit that. I am just again repeating the classification of equilibrium diagrams to refresh your knowledge here. So classification of equilibrium diagrams or phase diagrams, let us discuss in brief. They may be classified as follows. First is components completely soluble in the liquid state. Its subclassification part 1 is completely soluble in the solid state. They form the type 1. Next is insoluble in the solid state, that is the eutectic reaction type 2. Partly soluble in the solid state, the eutectic reaction type 3. Next is Formation of a congruent melting intermediate phase, they form the type 4. Next is the peritectic reaction type 5. Second classification type is components partly soluble in the liquid state, the monotectic reaction, they form the type 6. Next is components insoluble in the liquid state and insoluble in the solid state, they form the type 7. Apart from these transformations taking place in liquid state, there are many transformations which take place in the solid state. So we will be discussing in brief about the transformations which take place in the solid state. First is allotropic change. Next is order disorder change. Third one is the eutectoid reaction. And the last one is the peritectoid reactions. We will be discussing about all of them in separate presentations. In my previous video, I have discussed thoroughly in detail about the isomorphous systems, and my dear friends, I have made so many videos which are available in my channel. So I request you, all of you, to do visit my channel repeatedly and regularly so that you can watch all the videos available there, and also do watch all the videos from start to finish so that you can gain maximum knowledge about the subject. And currently in this presentation of video, I am going to discuss about the eutectic phase diagrams and systems. So we will be discussing about this in detail. So let us start the presentation for today. Eutectic phase diagrams. Very few systems exhibit an isomorphous phase diagram, that is, usually the solid solubility of one component in another is limited. Often the solid solubility is severely limited, though the solid solubility is never zero due to entropic reasons. In a simple eutectic system, that is binary, there is one composition at which the liquid freezes at a single temperature. This is in some sense similar to a pure solid which freezes at a single temperature. Unlike a pure substance, the freezing produces two solid phases, both of which contain both the components. So this is the difference between a pure metal freezing and a pure alloy freezing. The term eutectic means easy melting. The alloy of eutectic composition freezes at a lower temperature than the melting points of the constituent components. This has very important implications. For example, in the PBSN eutectic alloy melts at 183 degrees Celsius, which is lower than the melting points of both PB, that is plumbum, 327 degrees Celsius, and SN, that is stannum, 232 degrees Celsius. And this can be used for soldering purposes, as we want to input least amount of heat to solder two materials. We will be discussing about the PBSN eutectic phase diagram in detail in the coming slides. So this is the eutectic phase diagram of PB and SN. So as you can see, this is the temperature axis and this is the composition axis. Here as you can see that 327 degrees Celsius is the liquidus temperature of plumbum PB and 232 degrees Celsius is the liquidus temperature of stannum SN. And here at this particular point, that it has 62% SN, the eutectic reaction takes place as according to liquid while solidifying transforms to alpha plus beta, and this line is depicted as the liquidus line, above which the alloy is in liquid state, and between this liquidus and this eutectic line the present structure is alpha plus liquid, and at This side, this is liquid plus beta, and this 183 degrees Celsius solidus line, it is also the solidus line of the eutectic alloy having temperature of 183 degrees Celsius, below which the eutectic has the composition of alpha plus beta. So here at eutectic reaction at 183 degrees Celsius, liquid of 62% SN transforms into or solidifies into alpha of 18% SN and beta of 97% SN, as is depicted from these vertical lines at both ends. So again, considering the phase diagram of PBSN system, here there are three types of alloys which are formed. So type 1 alloy is having 63% SN and 37% PB. This is the type 1, that is having eutectic alloy. Type 2 alloy is 70% PB and 30% SN. This is the type 2 alloy. And third is 70% SN and 30% PB. This is the third alloy of type. Let us discuss in detail about all these things and describe the eutectic system in detail. It is seen that the solid solubility is limited for each of the two component metals, with alpha and beta representing primary solid solutions of different crystal structures. A straight line, the eutectic horizontal, passes through the three phase compositions alpha eutectic, liquid eutectic and beta eutectic at temperature T eutectic. This line is a collapsed three-phase triangle. At any point on this line, three phases are in equilibrium. During slow cooling or heating, when the average composition of an alloy lies between its limits alpha eutectic and beta eutectic, a eutectic reaction takes place in accordance with the equation L eutectic, that is liquid eutectic, transforms while solidification into alpha eutectic plus beta eutectic, and while on liquefaction it transforms alpha eutectic plus beta eutectic transforms into liquid eutectic while heating. The sharply defined minimum in the liquidus, the eutectic easy melting point, is a typical feature of the reaction. Consider the freezing of a melt of average composition 37 Pb and 63 Sn. At the temperature T eutectic of approximately 183 degrees Celsius, it freezes abruptly to form a mechanical mixture of two solid phases, that is, liquid L eutectic transforms on solidifying into alpha eutectic plus beta eutectic. From the lever rule, the alpha by beta mass ratio is approximately 9 by 11. As the temperature falls further, slow cooling will allow the compositions of the two phases to follow their respective solidus lines. My dear friends, I have made a separate presentation video on the lever rule which is available on my channel. You can visit that also for reference and clarifying your doubts regarding lever rule. Tie lines across this alpha plus beta field will provide the mass ratio for any temperature. In contrast, a hypoeutectic alloy melt, say of composition 70 Pb and 30 Sn, will form primary crystals of alpha over a range of temperature until T eutectic is reached. Successive tie lines across the alpha plus liquid field show that the crystals and the liquid become enriched in tin as the temperature falls. When the liquid composition reaches the eutectic value L eutectic, all of the remaining liquid transforms into a two-phase mixture as before. However, for this alloy, the final structure will comprise primary grains of alpha in a eutectic matrix of alpha and beta. I hope it is very much clear to you all. Similarly, one may deduce that the structure of a solidified hypereutectic alloy containing 30 Pb and 70 Sn will consist of a few primary beta grains in a eutectic mixture of alpha and beta. Low lead or low tin alloys with average compositions beyond the two ends of the eutectic horizontal freeze by transforming completely over a small range of temperature into a primary phase. Changes in composition are similar in character to those described above. When the temperature crosses the relevant solidus or solvus line, this primary phase becomes unstable and a small amount of second phase precipitates. Final proportions of the two phases can be obtained by superimposing a tie line on the central two-phase field. There will be no signs of a eutectic mixture in the microstructure. The eutectic, that is having 37 Pb and 63 Sn, and hypoeutectic having 70 Pb and 30 Sn alloys chosen for the description of freezing represent two of the numerous types of solders used for joining metals. So it is very much important how they form, which I have just described. Eutectic solders containing 60 to 65% tin are widely used in the electronics industry for making precise high integrity joints on a mass production scale without the risk of damaging heat sensitive components. These solders have excellent wetting properties which have contact angle of less than 10 degree, a low liquidus and a negligible freezing range. The long freezing range of the 70 Pb and 30 Sn alloy, that is called plumber's solder, enables the solder at a joint to be wiped while pasty. The shear strength of the most widely used solders is relatively low, say for example 25 to 55 meganewtons per square meter, and mechanically interlocking joints are often used. Fluxes, which are corrosive zinc chloride, non-corrosive organic resins, facilitate essential wetting of the metal to be joined by dissolving thin oxide films and preventing reoxidation. In electronic applications, minute solder preforms have been used to solve the problems of excess solder and flux. We are again considering the phase diagram of PBSN system. This alloy 1 is having 63% Sn and 37% Pb. This alloy 1. Alloy 2 is having 70% Pb and 30% Sn. This is the second alloy. And third alloy is 70% Sn and 30% Pb. This is the third alloy. This picture I have already shown, but here I have again mentioned it to describe something in more detail. So let us go. The above figure shows the sequence of structures obtained across the breadth of the PBSN system. Cooling curves for typical hypoeutectic and eutectic alloys are shown schematically in figure A of the next slide. Separation of primary crystals produces a change in slope while heat is being evolved. So in this current slide, a typical cooling curves for hypoeutectic alloy 2 and eutectic alloy 1 in figure below, and B is shown as dependency of duration of cooling arrest at eutectic temperature T eutectic on composition. So in this figure A, the alloy composition of 2, alloy number 2 is shown, cooling curve for the alloy number 2, and this is the cooling curve for alloy number 1. As you can see, as this alloy 2 freezes over a very small range of temperature, and as soon as the temperature reaches the T eutectic temperature, it abruptly freezes and solidifies completely. And for this eutectic alloy, as soon as the temperature lowers down, it abruptly freezes at temperature TE as soon as the temperature is reached, and it solidifies thereafter. And this diagram also shows the time versus composition. I hope it is very much clear to you all. Much more heat is evolved when the eutectic reaction takes place. The lengths, that is duration of the plateaus, are proportional to the amounts of eutectic structure formed, as summarized in figure B. Although it follows that cooling curves can be used to determine the form of such a simple system, it is usual to confirm details by means of microscopical examination, that is optical scanning electron and X-ray diffraction analysis. So now we are going to discuss about some microstructural characteristics of eutectic system. In this particular figure, the eutectic system of SN and lead is considered, and in this particular system it is again considered with two different types of eutectic alloys. We will be discussing them separately in the coming slides. But two important point here to note is that phase diagrams do not contain microstructural information, that is, they cannot tell you what is the microstructures produced by cooling. Often, microstructural information is overlaid on phase diagram for convenience. Hence, strictly cooling is not in the domain of phase diagram, but we can overlay such information keeping in view the assumptions involved. So again, considering the microstructural characteristics of the eutectic system, we will considering 18.3 weight percent SN, which is having less than C0 composition and which is having less than 61.9 weight percent of tin. So microstructure consists of crystals and a eutectic microstructure. So this particular point here, at this particular point, liquid is having LC0, that is weight percent of tin, and this particular where the solidus liquidus starts, the L and alpha are present. These are different denominations. So let us describe them. Just about TE, that is T eutectic, C alpha is having 18.3 weight percent stannum, C alpha is having 18.3 weight percent stannum, C liquid is having 61.9 weight percent stannum, liquid is having 61.9 weight percent stannum. So weight of alpha is equal to S divided by R plus S. S is this length, and R plus S is total this length. So it comes to approximately around 58%. And weight of liquid is equal to 1 minus weight of alpha, it gives 58%. So this is just about TE, means this particular line R and S. So it has been mentioned with different colors to differentiate them. And now let us consider just below TE, this portion just below TE. What happens? C alpha is having 18.3 weight% tin. C beta is equal to 97.8 weight% tin beta, and weight of alpha is equal to S divided by R plus S is equal to 72.6 weight%. So here the picture is clearly depicted with different colors to differentiate from each other, and weight of beta comes to 100 divided minus 72.6 is equal to 27.4 weight%. You can pause the video and observe this picture in more detail. What are the all phases present and their proportions. I hope we are going so far so good. Further explaining the microstructural characteristics of eutectic system. So in this second case, CO is equal to having C eutectic, means this particular eutectic alloy we are considering. So here microstructure represents eutectic microstructure, that is lamellar structure, alternating layers, that is lamellae of A and B crystals. So this is the eutectic point where the reaction is taking place, which is having C is equal to 61.9% tin and LC0 is weight% of tin, and which is the same as the C eutectic weight%. So the eutectic reaction takes place at 183 degrees Celsius. So different phases present here are mentioned. You can observe this by pausing the video. I have just explained the details of it. So now let us consider about hypoeutectic, eutectic and hypereutectic. What are these phases and where they are formed? Let us now consider. So as we consider this system at this particular point, this is the eutectic having 61.9% tin, and left side of this particular region, left side of this eutectic line, this region is called hypoeutectic, and right side of eutectic, this region is called hypereutectic. So my dear friends, it is very much important to clearly understand the concept of hypoeutectic, eutectic and hypereutectic. Normally many a times it is asked which region is called hypoeutectic, which region is called hypereutectic. So be clear which region is called what. So I hope I am making it very clear to you all. You can pause the video and observe all the phases present in each of the hypoeutectic, eutectic and hypereutectic structures. Let's move on. Now let us consider some further examples of eutectic system. We will consider the CUAG eutectic system. Raoult's law states that the freezing point of a pure substance will be lowered by the addition of a second substance, provided the latter is soluble in the pure substance when in liquid and insoluble when in solidified. The amount of lowering of the freezing point is proportional to the molecular weight of the solute. So you can again refer this picture having copper and argentum. This is the eutectic reaction. This is the eutectic temperature TE, and this is the C of that is the having the eutectic composition. All the variables are mentioned here. So here the limited solubility alpha is having mostly copper. This portion alpha is having mostly copper and beta is having mostly argentum. beta, this is having mostly argentum, that is silver. So T eutectic, it has no liquid below T eutectic, means this particular temperature, above this there is purely liquid and below this there is no eutectic below this temperature, and C is the minimum melting at T eutectic. So here three single phase regions, that is liquid, alpha and beta, exists at 71.9 weight% argentum at 779 degrees Celsius, commonly known as eutectic. The reaction is as follows: LCE eutectic, on solidification it gives alpha C alpha eutectic plus beta C beta eutectic, and while on heating the reverse reaction takes place. I hope the eutectic reaction is very much clear to you, all of you. The primary reaction states that while at eutectic reaction, liquid on solidification transforms into two solid phases, and these two solid phases on heating transforms into a common liquid. This happens at a particular temperature. I hope it is very much clear to all of you. So now we will be considering some special eutectic systems. So let us consider the eutectic system which is having without terminal solid solubility. For example, we will be considering bismuth cadmium system. Technically, it is incorrect to draw eutectic phase diagrams with zero solid solubility. This would imply that a pure component, say bismuth in the example considered, melts over a range of temperatures from P to 271 degrees Celsius, which is wrong. This is particular diagram which is depicted here, and this particular point P is considered and explained. Also, let us consider an example at a point P which lies on the eutectic line PQ. PQ, this is the eutectic line PQ. At P, the phases rule becomes F is equal to C minus P plus 1 is equal to 1 minus 3 plus 1 is equal to minus 1. How is it possible? So let us further describe it. So technically this is incorrect. There has to be some terminal solid solubility here. So the correct version of diagram with some terminal solid solubility is like this, having very slight terminal solid solubility. You can observe this video by pausing it and observe it very sincerely. Let me explain it further. So note the above is an alternate way of arriving at the obvious contradiction that at P, on one hand we are saying that there is a pure component, and on the other hand we are considering a three-phase equilibrium which can happen only for bismuth cadmium alloys. In eutectic systems, at eutectic point E, there exist three phases coexist, which are liquid, alpha and beta. The number of components in a binary phase diagram is 2, that is, the number of degree of freedom F becomes 0. This implies that the eutectic point is an invariant point. For a given system, it occurs at a fixed composition and temperature. My dear friends, please note this particular line. This is very much important. So I am again repeating this. This implies that the eutectic point is an invariant point. For a given system, it occurs at a fixed composition and temperature. I hope I am making it a very clear point to all of you, and all are understanding it very clearly. So now we will be discussing about the application of lever rule in eutectic systems. I will be explaining it with the help of some solved examples. Let us now first consider for a 40 weight percent tin, 60 weight percent Pb alloy at 150 degrees Celsius. Find the phases present alpha and beta, and composition of phases given is C0 is equal to 40 weight percent tin, Ca alpha Ca is equal to 11 weight percent tin, and Cb is equal to 99 weight percent tin. So this is the PBSN phase diagram. So right now we are considering here this particular point. So applying the lever rule in the eutectic system is explained in this diagram. This is the C0 40 weight percent tin. So we will be calculating the different phases present in this 40 weight percent tin phase alloy. So here weight of A is equal to S divided by R plus S. S is this divided by R plus S total length. So it comes to C beta minus C0 divided by C beta minus C alpha. So putting the values, 99 minus 40 divided by 99 minus 11 is equal to 59 divided by 88. It comes to 67 weight percent. Now weight percentage of beta comes to R divided by R plus S, R divided by R plus S total length. So C0 minus C alpha divided by C beta minus C alpha. Putting the values comes to 40 minus 11 divided by 99 minus 11, reduces to 29 by 88 is equal to 33 weight percent. I hope it is very much clear the application of lever rule in eutectic system. This is the one example. Let us now consider the second example. Second example is for a weight percent 40 weight percent of tin and 60 weight percent of Pb alloy at 220 degrees Celsius. Find the phases present alpha and the liquid. Composition of phases given is C0 is equal to 40 weight percent tin, Ca is equal to 17 weight percent tin, and C liquid is equal to 46 weight percent tin. Again considering the same PBSN phase diagram, but here the temperature has been risen. So here the temperature point is T is this. So we will be considering the various phases present at this particular temperature. So weight percentage of A is equal to Cl minus C0 divided by Cl minus C alpha. Putting the values, it gives to 46 minus 40 divided by 46 minus 17. So it reduces to 6 divided by 29 is equal to 21 weight percentage. And weight of liquid is calculated as C0 minus C alpha divided by Cl minus C alpha. Putting the values gives 23 by 29 is equal to 79 weight percentage. All the values are mentioned here. You can pause the video and observe the picture and calculate them by yourself to get the better clarity on the lever rule. Application of lever rule in the eutectic system. I hope I have made all the points very clear. So let us now further explain it with the help of another example. During the solidification of a eutectic PBSN composition C0, 90 volume percent of solid consisted of the eutectic mixture and 10 volume percent of the pro-eutectic beta phase. So here we have to calculate what is the value of C0. So my dear friends, these type of questions are also being asked in various exams where you have to calculate the C0 composition at which particular composition this will happen, like that. So here the given data is density data for beta and alpha is given as rho alpha is equal to 10,300 kg per cubic meter, rho beta is equal to 7,300 kg per cubic meter, and eutectic data is 183 degrees Celsius is the temperature of eutectic temperature, and 62 weight percentage is the content of stannum. So let us start with some observations. Lead, that is Pb, is heavier than stannum and Hence, the density of alpha is more than that of beta. Since the pro-eutectic phase is beta, the composition is hyper-eutectic towards the Sn side. I hope you can remember hyper-eutectic. I had just explained previously. The volume fraction in percentage are usually calculated by taking the area fractions by doing metallography, that is microstructure, and then converting it into volume fractions. Usually volume fraction is assumed to be equal to area fraction. So the reaction is liquid having 62.8% Sn. On solidification, it transforms into alpha of 18% Sn plus beta of 97% Sn, and the reverse reaction takes place while on heating. Using the fact that there is 10 volume percent of beta phase, so weight fraction of pro-eutectic beta is equal to weight of beta divided by weight of the alloy. Putting the values, it gives to 0.1 into 7300 divided by 0.1 into 7300 plus 0.9 into rho eutectic mix. So where P rho eutectic mix is equal to 10,300 into 97 minus 62 divided by 97 minus 18 plus 7,300 into 62 minus 18 divided by 97 minus 18 is equal to 4563 plus 4066 is equal to 8629 kg per cubic meter. So now substituting in equation 1, weight fraction of pro-eutectic beta comes to 0.086. So using the lever rule, 0.086 is equal to C0 minus 0.62 divided by 0.97 minus 0.62 is equal to, so C0 is equal to 0.650. So it comes to 65%. I hope this calculation is very much clear to all of you. Please don't get confused. If you are having any doubt, please do repeat the presentation and clearly understand each topic, each point very seriously, very sincerely. With this, I hope you like the content and found the video worth. So please don't forget to like, share and subscribe the channel. With this, I am taking my voice to rest, and I request you all to remember to press the bell icon so that you can get the notification of new videos promptly. My dear friends, thank you very much for watching this video, and once again I am thankful to all my subscribers who believe in me, like my content, share my videos to their friends. So once again, thank you very much. Do repeat my channel regularly and repeatedly. Do visit my channel. Do watch all the videos present there and like and share with your friends. Thank you very much.